Hello everybody. Over here, we are going to discuss mainly in three type of equations. One is the Cartesian equations, and second one is their corresponding parametric equation, and the third one is the polar equations of some standard curves. We are not going to discuss the total deduction of their respective equations. Rather, we shall study over here some properties of these standard curves and their equations. All right. So we know all these kind of standard curves like circle, parabola, then ellipse, hyperbola, etc. Now we shall study some equations like this kind of equations. These are called asteroid. Then we shall study cycloid and several other curves. And if we want to consider the Cartesian representation of this kind of curves, mainly we have two different kind of separate Cartesian representation. One such representation is called implicit form, implicit representation. What is this implicit representation? If a function is, if the curve of equation of certain curve is given by this kind of equation, then this kind of representation is called the implicit representation of a curve. For example, consider this kind of equation: circle x square plus y square is equal to a square. This is the equation of a circle. So if we consider, if we take this a square on the left hand side, then we shall have x square plus y square minus a square is equal to 0. So x square plus y square minus a square, this is our function capital F. So capital F of x comma y is equal to 0. That would be the implicit representation of a curve. And we need to remember that all the curves do not have this kind of representation. You see, y is equal to fx. Generally, we say that a curve can be written in this fashion: y is equal to fx. But all the curves do not have this kind of representation, and this kind of representation is called explicit representation, and this kind of representation is called implicit representation. So this is the example of implicit curve. Over here, this is the equation of a parabola: y square minus 4ax is equal to 0. And over here you see this equation can be written in this fashion, that x is equal to y square divided by 4a. Got it? So you can say that I have written x is equal to some function phi of y in this way. So either you will have to represent it in the form of y is equal to fx, or you will have to represent it in the form of x is equal to pi y. These two representations are called explicit representation. Got it? And you may ask, sir, we could also write this equation of the parabola in this way. Say y is equal to plus or minus y is equal to plus or minus root over of how much, 4ax. You could also write it in this way, but the problem is that generally the definition of function says that if we want to represent it in this fashion, it would not be a function. Why it is not a function? Because the definition of the function says that this kind of function f is a function when for a single value of x we get a single value of y. Got it? For every value of x, if we get a single or unique value of y, then only we say that f is a function. Otherwise it is not a function. It would be a relation, one to many relation, not a function. Okay, you might have studied this relation and functions in set theory. We what we get over here, that for suppose if we put x is equal to suppose 1, In that case, you will get for plus symbol and for minus symbol, you will get two different values of y depending on this plus and minus. Got it? So for a single value of x, you will get two different values of y. But the definition of function says that for a single value of x, we will get a single value of y. So this kind of representation will not be the representation of a function. That's why we represented this equation of parabola in this fashion. X is equal to y square divided by 4a. Got it? X is equal to y square divided by 4a. If you look at this expression, for a single value of y, you will get a single value of x. No problem is there. So if you want to represent this equation of a parabola from from implicit to explicit form, this would be the representation, maybe some function phi of y. Got it? So whenever the function is represented either in the form y is equal to f of x or x is equal to phi of y, then only the representation is called explicit representation, and most of the times it is not always possible. That's why we study this kind of implicit representation of a function or implicit form of a function. No harm is there in studying a function in its implicit form. Most of the functions are implicit. You see the equation of a circle, the equation of an ellipse, then equation of a hyperbola. These are all implicit expressions. And we shall study a few other curves in this chapter. This is the curve that is called asteroid. This is the curve that is called FOLIUM of Descartes. This is the semi-cubical parabola. This is the lemniscate of Bernoulli, etc. We shall study a few of these curves, so some standard number of curves out of this. So these are all implicit representation of a curve of different exam of different curves. Now we consider explicit representation. You see, as I told you, y is equal to fx or x is equal to phi y. These are implicit representation. So x square, x is equal to y square, or x is this kind of expression. X is equal to y square, or y is equal to x square. This kind of representation. These are the explicit representation of parabola. This is one more curve that is called catenary. You see, this is this kind of curve. These are called rectangular hyperbola. Y is equal to 1 by x. So these are actually examples of explicit curves, explicit representation of a curve. And most of the time, apart from these two representations in explicit and implicit form, we also study the parametric representation. For example, if you consider this circle, x square plus y square is equal to a square. This circle can be represented in parametric form over here, like x is equal to some function of the parameter t. Over here, x is equal to a cos t. Similarly, y is equal to another function of the parameter t. Over here, y is equal to a sine of t. So altogether, these two expressions, x is equal to a cos t and y is equal to a sine t, this representation is called the parametric representation or the parametric equation of the circle x square plus y square is equal to a square. And if you consider the range of this parameter for a single for one rotation of the circle, the range should be from 0 to twice pi. Okay, so these are some standard results of parametric representation of a curve. If you consider ellipse, this kind of ellipse x square by a square plus y square b square is equal to 1, then it can be written in this form: x is equal to a cos of t, y is equal to b sine of t. So this is this is a parametric representation of ellipse. Similarly, we can have the parametric representation of hyperbola and other kind of curves. This is a parametric representation of parabola. You all know this representation. So I'm just going through the results only. I'm not discussing anything extra out of this part. Say if you consider this hyperbola, x is equal to a cos hyperbolic t, y is equal to b sine hyperbolic t. So these are the some standard expression of the parametric representation of hyperbola. You see, hyperbola can be written in a different fashion. Say it may be x is equal to a sec of sake of maybe another kind of parameter, consider theta, and y is equal to b tan of theta. Hmm. So this kind of parametric representation is also possible. So what you observe over here, that a single curve may have two or more different parametric representations. What I am trying to say is that the parametric representation of a curve is not always unique. You may get different parametric representation of a single curve. Got it? This is a curve that is called cycloid. Now, how did we get the cycloid? The total deduction has been written over here. I am not going through the deduction. Rather, I am going through the parametric representation of this kind of curve. When x is there, x is can be written to be equal to x is equal to a into t minus sine of t, and y can be proved to be equal to a into 1 minus cos of t. And what is this? This is the curve from O to the point V, and then V to the point O prime, and so on. It is actually an infinitely extended branch, and the this portion, this is a segment of the curve, and similar segment, just you can copy and paste this curve, and on the left and right side you will get an infinitely extended curve. And this is the equation that has been written over here. X is equal to a into t minus sine of t, y is equal to a into 1 minus cos of t. Now, in order to explain this, how did we get this kind of curve? What we actually do? Actually, we consider a circle, or or you can consider a tire of a cycle. Now, in this kind of circle, if one point P is fixed, Hmm? Suppose you get a marker pen and mark this point by some red color. Got it? And now slide this circle along this surface, hmm, along x-axis. Okay. Now try to slide this circle, or you can say try to rotate this circle along x-axis. Then the rotation, along with the rotation, the locus of this point P will generate this curve. This curve is called the cycloid. And to understand this in a better sense, let me show you a picture over here. You see, if you look at this picture, this is a page from Wikipedia. If you look at this picture, you can understand that just one circle is rolling along x-axis, and a point on that circle is fixed, and that fixed point is generating this kind of curve, and that is called the cycloid. So this is the cycloid, one kind of curve. Now let's move to another kind of curve. I told you that the circle may roll along this kind of axis, but just consider a different kind of situation. Suppose the circle is rolling below this kind of axis. Hmm. Along x-axis, just it is touching this x-axis, or you can also consider it in this fashion. The circle is rolling along this line. It is always touching this kind of line. In that case, you see the curve on this kind of point would generate a similar curve like this. Hmm? A similar curve like this, and this kind of curve is called inverted cycloid. Got it? Let me show you through another example over here. This kind of curve. You may get this kind of curve over here. The this curve along the circle is rotating along this curve. Got it? And this kind of curve are called inverted cycloid. This is the example of inverted cycloid. And there are few other similar examples as well. This is a cycloid, and this is another inverted cycloid, it has different kind of representations. You see, you just need to remember that whenever both of these two symbols, whenever both of these two symbols are positive, along and negative, both of these are positive or negative. Either both of these are positive or both of these are negative. In such case, you would get ordinary cycloid. And if one is positive and another is negative, you look at this, one is positive, another is negative. You can also consider this kind of equation over here. This is the first one is negative, second one is positive. So in such cases, you will get this kind of inverted cycloid. In this first case, you will get this kind of inverted cycloid, and in this second case, you would get this kind of inverted cycloid. Got it? So these are some examples of inverted cycloid. Hmm. Let's move to the next curve, that is called asteroid. Hmm. What is asteroid? And the asteroid is this kind of curve. And how did we get this asteroid? Let me show you the technique of getting asteroid. This is the curve asteroid, and look at this animation over here. This red curve is called the asteroid. You can see one circle is sliding inside a large circle. The radius of one circle, this is the radius, and it is moving along another circle. And in this way, we get the the curve, the red curve, that is called the asteroid. Got it? So this is the example of asteroid. And what would be their mathematical equation? Let me show you the mathematical equation. And the mathematical equation of asteroid is this kind of equation: x to the power of 2 by 3 plus y to the power of 2 by 3 is equal to a to the power of 2 by 3. A is a parameter or a positive constant. And this asteroid can be written in parametric form. This is the Cartesian form. Got it? And this asteroid can be written in parametric form in this way: x is equal to a cos cube t, y is equal to a sine cube t. Okay, please remember these two representations, because this would be useful in your subsequent study. Hmm? X to the power of 2 by 3 plus y to the power of 2 by 3 is equal to a to the power of 2 by 3, the Cartesian form. And the parametric form is x is equal to a into cos cube t, and y is equal to a into sine cube t. And in order to get the total asteroid, this would be the range t from 0 to twice pi. Got it? Over here, t should vary from 0 to pi in this first quadrant. In the second quadrant, not from 0 to pi, would vary from 0 to pi by 2 in the first quadrant. In the second quadrant, it would vary from pi by 2 to pi. In the third quadrant, it would vary from the t would vary from pi by 2 to 3 pi by 2, and in the fourth quadrant, it will vary from 3 pi by 2 twice pi. So remember the part of this asteroid in the different quadrants. Got it? So these are the detail about asteroid. Next is the FOLIUM of Descartes. This kind of equation: x cube plus y cube is equal to 3a xy. And this FOLIUM of Descartes can have this kind of parametric form: x is equal to 3at divided by 1 plus t cube, y is equal to 3at square divided by 1 plus 1 plus t cube. This kind of curves, these are called FOLIUM of Descartes. And this is the this curve over here. You see the curve over here is moving along this direction, and after coming to the center, it is moving along this direction. And after one rotation, it is moving along this direction. This is called the FOLIUM of Descartes. Properly speaking, you can search over here the FOLIUM of Descartes. The FOLIUM of Descartes, you would get the curve, that is this kind of curve. You see this green curve. This is the FOLIUM of Descartes. But it is firstly it has actually two infinite branches. One is in this second quadrant and another is in the fourth quadrant, and one rotation is there in this first quadrant. You can call it a loop. Hmm. Loop of FOLIUM of Descartes, and this FOLIUM of Descartes is passing through the origin, so it is actually carved through the origin. And if we draw this kind of straight line, this kind of straight lines are called asymptotes actually. And the distance between this curve and straight line, this distance would ultimately would tend to zero as we move towards infinity. This kind of curves are called asymptotes of this FOLIUM of Descartes. An equation of this kind of dotted curves or dashed curve, this kind of equation, that would be you see, this would be the equation x plus y plus a. One can prove that equation of that kind of asymptote would be x plus y plus a is equal to 0. Now let's move to some curves related to polar coordinates, and what would be the polar as well as the Cartesian representation of those curves. Polar coordinates means in terms of the polar coordinates r, and the radius vector r and the vectorial angle theta, we will have to represent the equation of this kind of curves. So such curves are called to have a polar equation. The first curve we shall consider over here. You see, a circle can have this kind of polar representation. R is equal to some constant A. A is the radius. And the first important curve that we shall discuss over here is this curve, cardioid. It is just like the shape of a heart, cardiac. All right, that's from that term we have this name nomenclature, the cardioid. What is the equation? It can have two different equations. R is equal to A into 1 minus cos theta. This is the curve. R is equal to A into 1 minus cos theta. And over here, R is equal to A into 1 plus cos theta. This is the curve. So both of these two are called cardioid. But over here, how does this cardioid is generated? Let's check the generation. This red curve, you see, when one circle is sliding on another, this kind of curve, these are called cardioid. Clear? And over here, you see this position. This can be written in terms of polar coordinate, the red curve. How to write them in polar coordinate? These are the expressions. And if you consider any point over here, if you consider any point over here, say this is a point P, all right, with with radius vector r and vectorial angle theta. Okay, then we can draw a straight line from the point P to this pole O. O is the pole in the polar coordinate system. And what would be theta? You see, this would be the angle theta. This would be the angle theta. Got it? So you see, whenever P is situated in this zone, in this zone, when P is situated in this zone, you see, let me magnify this curve a bit. Whenever P is situated over here, if this is the position of P, then this kind of straight line, that would be the radius vector. Got it? And this angle would be the angle theta. And therefore, in this kind of case, whenever P is the position, you see over here, theta would be, this theta would be less than pi by 2. In fact, when P is situated at this point O, theta would be is equal to 0. And as P increases along this curve, theta would increase. And theta would increase up in positive direction. So this much up to this much, up to this much. Let me write. Let me draw a straight line over there. Up to this much. Hmm. Up to this much, theta would be less than pi by 2. But whenever p increases further, theta would increase, and then theta would become greater than pi by 2. Got it? And over here, when p would again come over here at this point, over here at this point, up to this level, theta would be greater than pi by 2. In this range, theta would be greater than pi by 2, and that is less than pi. Clear? Theta would be greater than pi by 2 and less than pi. And further, when the point P moves along this direction, hmm, along this direction, up to this point, up to this kind of point, just we can draw a perpendicular line. Got it? In that case, pi would be less than theta, and that theta would be less than 3 pi by 2. Okay, and in this zone, whenever p would further increase and again come back to this pole O, then 3 pi by 2, this 3 pi by 2 would be less than theta, and that is less than twice pi. So please remember this kind of results, that in these four zones, the range of theta over here, of course, theta is positive, but less than pi by 2. In this zone, theta varies from pi by 2 to pi when p moves along this direction. Up to this point, theta is less than or is equal to pi. We can write an equal to over here. And in this zone, theta is greater than pi and less than is equal to, suppose, 3 pi by 2. And in this zone, theta is greater than 3 pi by 2 and less than twice pi. So in this fashion, theta would change. And similarly, in this cycloid as well, over here you see, in this zone, whenever p increases up to this much, say a 90 degree, making an angle of 90 degree, this much zone. Over here, theta would vary from 0 to pi by 2. In this zone, then pi by 2 up to pi along this direction, whenever up to this point O, up to pi, and then again further, then pi to 3 pi by 2 up to this zone, and then 3 pi by 2 to again twice pi up to in this zone. So in this fashion, theta would change. So you need to remember the range of theta. Got it? That is the point you generally require to remember in different problems, because in subsequent problems you sometimes need to integrate within certain specified range. Then how to know the limit, the lower limit and upper limit of theta. That limit you need to remember. Next, we consider the curve that is called lemniscate of Bernoulli. R square is equal to a square cos of twice theta. Or it may have a Cartesian form, but the Cartesian form is a very difficult to remember. This is the Cartesian form. So we mostly consider this kind of polar form of the equation. R square is equal to a square cos of twice theta. This picture you see over here, this is a kind of process related to hyperbola. One mechanism has been shown through this picture. One point on this straight line is taken fixed, and as we change the position of straight line related to certain conditions, of course, in that case the red curve generated over here, that is called lemniscate of Bernoulli. and this blue curve is actually an hyperbola. Hmm. And related to this hyperbola, we get a curve that is called the lemniscate of Barnum. And what is the equation? This is the equation: r squared is equal to a squared cos of twice theta. So in this fashion, we get the lemniscate of Barnum. Hmm. And again, you see over here, this it has actually two loops. One is this loop, and another is this loop. So okay, so we don't have any portion of the curve in this zone. And what for did we have this kind of straight lines? Just in order to highlight the range. Over here, you see, if you consider any point, let me magnify this curve a bit over here. If you consider any point in this zone, suppose you want to find out or you want to make certain integration over this kind of curve, then how to how to get the range of the vectorial angle theta. If a point P is situated over here, you see generally theta is always measured from the positive x-axis. Got it? Or the initial axis. So if you consider this point O as the pole and this axis as the initial axis, in that case theta has to be measured from this OX straight line. Now in this zone, this straight line is actually a straight line making an angle of 45 degree with positive x-axis. This is a straight line making an angle of 45 degree with this positive x-axis. So whenever you just need to draw or you need to make any integration, you need to perform any integration. In that case, theta would be of course greater than 0. That would be the lower limit. And what would be the upper limit over here? You see the maximum angle would be this much. This would be the maximum angle. Got it? So that maximum angle it becomes is equal to pi by 4, 45 degree. Got it? And so in this zone, the range of theta should be 0 to pi by 4. So whenever this point P is moving along this direction through this point P and coming to the pole or the origin over here, in that case theta would vary from 0 to pi by 4. Next, in this portion, in this segment, whenever P is varying in this zone, in that case, theta would vary from pi 3 pi by 4. Why 3 pi by 4? 3 pi by 4. Why 3 pi by 4? Because you see this angle, this straight line is making an angle of 3 pi by 4 with this positive x-axis. So if you consider any point P on this zone, in this kind of position, in that case, this angle of the radius vector, this angle of the radius vector, this angle will be greater than 3 pi by 4. That's why we have this kind of limit from 3 pi by 4 to maximum. It may come with to this point capital A, and at the point capital A, this vectorial angle is equal to 180 degree or pi. Got it? 180 degree or pi radian. So the range of theta would be from 3 pi by 4 to pi radian. I am representing everything in terms of radian. Therefore, theta would vary from 3 pi by 2 to pi in this zone, in this part of the second quadrant. Got it? We do not have any portion of this curve in this zone. We do not have any portion of the curve in this zone of the second quadrant. Similarly, we do not have any portion of the curve in this zone of the first quadrant. Got it? And now after the point capital A, again if we consider this zone over here, suppose the one point P is moving along this direction, then what would be the range of theta from the point capital A? At the point capital A, the value of theta was equal to pi. This was the angle 180 degree. Got it? Therefore, this would be the lower limit pi less than theta, and less than how much over here? Less than this much angle. What is this much angle? Pi plus pi by 4. That means 5 pi by 4. 5 pi by 4. So in this fashion, you will have to identify the range by looking at this picture. 5 pi by 4. Because this much angle is equal to 5 pi by 4. This much angle is equal to 5 pi by 4. Got it? And again, in this zone, there is no segment of the curve. In this zone, there is no segment of the curve. So after coming to this point along this direction, to the point O, if further P arbitrary point wants to trace the remaining portion of this segment, this much, then you see this would be the guiding straight line. And in this, what is the angle made by this kind of straight line through this positive direction of the initial axis? This much angle. What is this much angle? This angle is actually equal to, this angle is actually is equal to 7 pi by 4. And if at this point A, the total one rotation is complete. At this point A, one rotation is complete. That means twice pi radian rotation angle is been traveled. And therefore we can say that this is less than theta, and that is less than twice pi. So in this fashion, you will have to remember their range. So twice by this much. So in this way, you will have to remember their range. So in this zone, theta would vary from 0 to pi by 4. This is 0 is lower limit, pi by 4 is upper limit. Then no range is there in this zone. No segment of the curve is there in this zone. So forget about this zone. Then theta would vary from 3 pi by 4 to pi. Got it? Afterwards, the theta would vary from pi to 5 pi by 4, and no segment is there in this zone. So forget about these zones. And afterwards, then theta would vary in this portion of the fourth quadrant. Theta would vary from 7 pi by 4 to twice pi. So in this way, we get the different variation of theta as the point P moves along this kind of curves. That is called the lemniscate of Bernoulli. And we discussed this kind. We have one more or one or two special kind of curves. These are called polar this equations of this kind of curve. R to the power of n is equal to a to the power of n cos of n theta. This kind of curve, whenever n is equal to 1, we get a circle. This would be the equation of circle. And whenever n is equal to 2, we get the lemniscate of Bernoulli, this kind of equation. So separately, we have studied many of these equations. This kind of equation, this kind of curves, these are called spirals. Particularly, there are several kind of spirals. Particularly, one spiral that would be very useful for us. That is called equiangular spiral. This kind of spiral, equiangular spiral. What is the equation of the curve? R is equal to A into e to the power of theta cot of alpha. This kind of curve. R is equal to A into e to the power of theta cot alpha. This kind of curves are called equiangular curve or equiangular spiral. Why equiangular? Because you see, this is the curve of that spiral. If you consider the pole over here, and it can be proved that the radius vector always makes an angle alpha with the tangent line. This line is the tangent line at the point P. Got it? So this angle is always a constant quantity alpha, and this alpha comes in this equation. A into e to the power of theta cot alpha. This is called the equiangular spiral. This is called the equiangular spiral. And there are other several spirals like spiral of Archimedes and all. We don't need to study all these reciprocal spirals and etc. Hmm. This is what particular kind of curve that is called the rose petals. You would get this kind of curves in subsequent problems. What does it say? It says that r is equal to a sine of n theta. This kind of curve where a is greater than 0, and it can be shown that whenever n is an odd positive integer, hmm, whenever n is an odd positive integer, it would have n number of loops. These three are called loops. Hmm. And whenever n is an even positive integer, hmm, suppose n is equal to 2, then we will have twice n number of loops. It may be n, it may be is equal to 2, n may be is equal to 4 or 6, etc. Then we will have twice n number of loops. For example, over here, this is the equation where you see n is equal to 2. This n is equal to 2. R r is equal to a sine of twice theta. If you consider this model over here, just n has been taken as equal to 2. Clear? And in this kind of curves, let me magnify this one a bit. In this kind of curve, r is equal to a sine of twice theta. You see, we have four different loops: 1, 2, 3, 4. And in this kind of curves, in this curve or this curve, whatever you consider, you would observe that this angle, this much angle, this much angle, and this much angle, this total angle must be is equal to the sum of this angle, and this angle. Got it? The angles inside the loop and outside the loop, both of these, the sum of these two angles are same. That means this angle, their total, and this angle. The total of these three angles must be is equal to 180°, and the total of this angle and this angle, that would also be is equal to 180°. Got it? And therefore, if you want to draw a straight line like this, you see, I told you that the sum of this angle plus this angle and this angle, this total is equal to 180°. That means individually we can say this angle must be is equal to 60°. That means this angle should be is equal to 60° or pi by 3. Got it? So this angle is pi by 3. Pi by 3. Got it? So pi by 3, then similarly we can pi by 3 to 2 pi by 3 we get this much, and then from 2 pi by 3 to pi we have this much angle. Got it? So in this way you will have to remember their range. So 0 to 3 pi, and then in this zone, in this zone, 3 pi by 2, twice pi by 2 to pi in this zone, and then again this much is not present in the curve. Then over here, how much angle should we consider? You just have to measure this angle: 60 degrees, 60 degrees, 60 degrees, 60 degrees. So 4 into 60 degrees, that means 240 degrees. 240 degree up to how much? Over here, 5 into 60 degree, that means 5 into 60 degree, that means 300 degree. So in this way you will have to find out the range of theta. Got it? So in this fashion you will have to identify the range of theta. So altogether, the total 360-degree angle has been divided, and over here again similar computation comes over here. You see, this much angle and this much angle should be equal to this much angle. So this is actually the total. This is 22 and a half degree. This is 22 and a half degree. Altogether 45 degree. and that 45 degree is equal to this much 45 degree. Got it? So if you want to compute the range, you will have to draw two straight lines. The range or the range of theta, you will have to draw this kind of two straight lines. This angle, this straight line will have the angle 22 and half, and this would be 22 and half plus 45 degree. So accordingly, you will have to compute the range of theta. Similarly, you can draw two straight lines over here, this kind of straight line and this kind of straight line, and accordingly you will have to compute and find the range of theta over here. Hmm. So that these are the observations that this angle, this is this total, this angle, this is the angle, this much do not lie inside the loop. Hmm. So again, this angle, this is 45 degree, this is 45 degree, this much angle is equal to 45 degree, and this much angle is equal to 45 degree. So in this way, you will have to compute the angles over here. This is for n is equal to 2, mind it. This is for n is equal to 2. And suppose for n is equal to 4, I told you whenever n is an even number, we will have twice n number of pedals. These loops are called pedals. So similar, just like a flower, whenever we have a pedal. So if n is equal to 4, and then we shall have twice n, that is equal to 8 number of loops or 8 number of pedals. What would be the picture of for n is equal to 4? Let me show you the picture. This would be the picture. You see, 1, then afterwards you will get this second loop, 2, then 3, and then 4, not 1, this one, then 4, and then again come back to this 5, and after one loop it would come back to this 6, then one more loop it would come back to this 7, and then 7 would come back to this 8. So in this fashion, you ultimately all the total 8 loops will be generated. You will get one more equation. This is called catenary. Y is equal to c cos oblique x by c. That is the Cartesian form, and this is the parametric form. So that much knowledge should a student have in order to move forward with this kind of curves.